Yeah, stop me. Okay. Um, sorry. Okay, so first question. I'm just gonna quickly go over the setup and like clarify things. So one, there's a child named Li ah, Little. Okay, let's say Lily. Okay, so we have day 1 and day 2 and day 3. So day 1, 2, 3. And we have a chocolate on day 3, and we have a marshmallow on day 1 and day 2. Okay, so here is a table. I think doing a table, it's the easiest way. So day 1, day 2, and day 3. So Lily can either consume the marshmallow right now and don't get the hot chocolate in day 3, or she could potentially save all marshmallows and get a hot chocolate at day 3. So okay, so utility of consume. If Lily consume marshmallow on day 1 and day 2 and day 3, what will her utility be? It would be day 1 when she obtained the marshmallow, and day 2 when she obtained the marshmallow. And day 3 she gets nothing. Okay. Utility of saving would be day 1, you save, you don't consume, so there's 0 utility. And day 2, same thing. And day 3, you have 2 marshmallow plus 2 units of utility from the hot chocolate. Okay, so let's look at A. Suppose he's an exponential discounter, delta equals 1. Okay. Which of the following is his optimum plan on day 1? Save marshmallow for the hot chocolate or consume marshmallow as they arrive? Okay, so we have a two type of decision, right? Either you consume or you save. Okay, and we have a discount of 1. So UC will equals to, let's do like, this is day 1, this is day 2, this is day 3. So U of consumption is 1 plus delta 1 plus delta of 0. U of saving is equals to 0 plus delta of 0 plus delta square of 2 plus 2. Okay, so which of the following is his optimum plan on day 1? So optimum plan for the utility for consumption is 1. The utility of saving is 4. So UC is less than US. Therefore, save. Okay. Now move on to B. Suppose he's a hyperbolic discounter, which with delta equals 1 and beta is less than 1. So we don't know beta, but we know delta. Beta is something less than 1. From day 1's perspective, what's his discount utility of saving marshmallow for hot chocolate? Okay. So discount utility for saving marshmallow for hot chocolate. Okay, so that's U of S. So U of S equals to 0 plus beta. Let me just like make it cleaner. So day 1, day 2, and this is day 3. Beta of delta 0 plus delta squared of 4. This equals to beta 4. And U for consume is 1 plus beta delta of 1 plus delta 2 of 0, which equals to beta 1 plus beta. E. And that's it. That's how you set up for B1. Any question? No?
Wait, so the hyperbolic discounter still decides to save because 4 beta is supposedly greater than 1 plus beta.
How do you know?
Depends on the
Oh,
value
okay.
of
Yeah.
What if my
Uh-huh.
beta is 0.00001?
Oh, okay.
Right. So we don't know yet. We don't know whether or not the decision of choose to save or consume, like that depends on beta. Right. But we were not given beta. It just give us a range of beta. Yeah. I think that's what part C is asking. Part C is asking, for what value of beta will he prefer to save the marshmallow for the hot chocolate, right? So what value of beta will be US is greater than UC? Simple. Just plug it in. B4 is greater than 1 plus B, which equals to 4B greater than 1 plus B, which is 4B minus B greater than 1. So, wait, am I making a mistake? 3B greater than 1. B is greater than 1/3. Oh, is it correct? I'm not sure.
Yeah, I think it
Yeah.
is.
That's right.
Okay, yeah, just check my answer if I'm making a mistake, because I'm like doing it while not looking at anything.
Yeah, I think 1A UC is equal to 2, but the
Hmm?
rest seems fine. 1A, the
Wait,
utility of consumption, yeah, it's equal to 2.
oh, my bad. I think I missed the one on day 1. Yeah, nice catch. Yeah, sorry. Okay, great. So that's how you find the beta. If beta is greater than 1/3, you would prefer saving than consumption, right? But if beta is less than that, that means you discount more into the future. Therefore, you will rather consume now. So the lower the beta, the more you want to consume now. The higher the beta, ideally you want to save it for the future. It's pretty possible that the beta is greater than 1. So it's not bound to anything. but in this problem, it's bounded, it's within 1. Okay, so let's look at D. So, okay, we found that. Even if his day 1 self prefer to save, he might not be concerned that his day 2 self will not comply. After all, he has saved the marshmallow on day 1, and his day 2 self has the option of consume both right away. Okay, so let's take a look at this graph. Well, not even graph. It's just a table. And it's a crappy table. You can put more stuff to make it prettier, like beta, delta, and then look more complex, but I think this is okay. Okay, so at day 2, let's assume that this person is already saved. So let's create this U of save day 1. Then your day 1 looks like 0, and your day 2, if you save, it will be 0, and day 3 will be 2 plus 2. But let's put this day 2. Yeah. Okay. If you consume on day 2, it will be you save for day 1, of course. But at day 2, if you consume at that day, you get 2 units, and you get 0 on day 3. All right, so we're actually comparing this too. Ah, yeah, my arrow is bad. Okay, so at day 2 with this box. Okay. Yeah. So for what value of beta will he prefer to save the marshmallow on day 2 versus consuming them right away? So US2 is greater than UC2. So US2, which is beta 2 plus 2. UC2 equals to 2. So we set them greater. So US, it's 4 beta greater than 2. Beta is greater than 1/2. That's it. So at day 2, if your future discount is 1/2, well, if it's more than 1/2, you will comply and do the saving. If it's less than 1/2, that means you discount more. You can't fight the temptation of eat it right now, because you discount the future value is 4, right? Yeah. Okay, so let's look at E. Stop me if you have any question or anything. Okay, we're good. Okay, let's look at E. Let's suppose beta equals to 3, 4. At this value, he preferred to continue save on day 1 and day 2. And Lily's parents, being an asshole, don't want to pay that high premium on the hot chocolate, and then decide to give cheap marshmallow to Lily to attempt to skew her away from saving, so that she can consume all the marshmallow now. So this is what this question is asking. So the parent will offer her, let me just move this. Maybe I should just keep using the table. Table is pretty useful. Okay, so let me just erase this. So we're still at day 2. Her parent wanna offer Lily a certain amount, so that certain amount of marshmallow, so that she will consume on day 2 rather than day 3. Because day 3 the parent will have to buy hot chocolate that it's worth a gold. So for saving, that will be if Lily fight the temptation, would be 2 plus whatever the X amount of marshmallow that parent offer, and plus 2 units from the hot chocolate. If Lily save. If she does not save and fall into the temptation, she will consume and get a utility of 2 plus X amount of marshmallow that her parents offering. Okay. Now we're at day 2. We're trying to figure out what's the amount of X that yeah, I should probably just like in this case, like you should probably add like all the beta and delta in it, so it's like clear. Okay, we're at day 2. Okay, so at what value of X is Lily gonna choose UC2? So UC2 must be greater than US2. All right, so therefore 2 plus X is greater than beta, which is the discount value of if in the event of she save. So this 2 is from saving from the previous 2 day, and this X is the actual amount, and this 2 is the hot chocolate. Hot chocolate. Marshmallow. This is marshmallow to infinity. No, but anyway, and then you solve. So 2 plus X greater than 2 beta plus beta X plus beta 2, which is 4 beta plus beta X greater than 2 plus X. And plug in the beta, which is 3/4. So 3/4 or 4 plus 3/4 of X greater than 2 plus X. Cancel out. We got X. So minus 2. Minus 2. X is greater than 3 minus 2 plus 3/4 X. Plus 3/4 X, it's minus 3/4 X. So it's 1/4 of X is greater than 1. We got X is greater than 4. So the amount of the marshmallow parent have to offer is 4. So that Lily will consume more. Well, Lily will consume right away rather than save, because her discount, future discount beta is 3/4. Does that make sense? Am I recording? I think. Okay. Any question on this?
We're able to use decision trees for this type of problem too, right?
Yeah, I mean, this is basically decision tree, right? Like Lily, like you save or you consume, and then you have some like value or outcome of the saving and outcome of consumption. Right. So it's basically because you are day 2, it's the same thing. It's 0. Oh no, consume is 2 plus X, right? And then, oh no, that's saving. Oh my god, why is not working? 2 plus X And then US2 is 0. Well, this should be plus beta of 0, right? This is day 2. This is day 3. And then this is like, if you save, then your day 2 is 0. And then you plus a beta discount of future value, which is 2 plus 2 plus x. Right? And then you set them that UC is greater than US. It's the same thing. You'll get the same answer.
Okay, thank you.
Coffee is so good. Oh my God. I bought this like Costco coffee that's like dark roast. When you don't add milk, it tastes like burnt wood. Okay. Okay, let's go F. Explain in words why such a trick will not work on the exponential discount with delta equals 1. Discounted, right? So if you are not hyperbolic, then you only have delta, right? So beta, it's the hyperbolic. Let me see if I can draw this. So this should look like this. You should always add. In day 1's perspective, this is now. And then you should add delta and beta. Like delta squared, beta. Yeah, add all of them into these boxes, but I just don't want to. But if you are not hyperbolic, so the beta is gone. Now you only have a delta. If your delta equals 1, then you will have an equation that looks like this. So US2, well, decision of consumption and then decision of saving. So you have 0 plus delta of 2 plus 2 plus x. And then you have this, which is current at day 2, will be 2 plus x plus delta of 0. And then you have to set them equals to each other. Well, not equals to each other. You want to force that decision to push it this way, right? So UC2 must be greater than US2. So we'll have UC2 is greater than US2. And let's see if that's the case. So it's 2 plus x greater than delta of 2 plus 2 plus x. If delta equals 1, we'll have 2 plus x greater than 4 plus x. So no matter how much marshmallow you give it to this person, if he or she does not have any discount, then like you can give me infinity, I will still save and then consume on day or consume the hot chocolate at day 3. Right? Yeah. So, yeah, I'm not gonna try to solve this because it's not solvable. X is like infinity. Okay, so let's go to question 2. Any question on question 1? No? Okay. Let's start question 2. Suppose Lily has an older sister named Big. I don't like the naming. Okay. So Big has a full-time job that pays money of M. Monthly? Oh, monthly salary of M. Okay, so it's paid the first of every month. In each month, she experienced a utility right after her salary is paid. Assume her utility is based on the standard prospect theory value function. Okay, so standard value prospect theory function. It looks like concave up. Something like this, right? Oh my God. Okay. Something like this. The value function, v of x, x. So at the center, we got, so with a reference point set at M. So this is our reference point. It's set at $M. Okay. Each month. Yeah. Okay. Concave in gains, convex in losses. Exactly is the graph. Okay. So let's go to question 8. Bonus. $12,000. You have 2 decisions. You can take it now. Take it later. Okay. What's the value of taking now? So the value of taking it now is V of 120. What about you take it later? So take it later would be you're taking $100 installment every month. Right? This, your value function will equals to sum of I equals to 0 to 12 of value of xi. So which is 12 times V of 100. Right? So every month you get 100. And the sum of all that 100 gives you like this yearly value function. Value of happiness, I guess. Does it refer to as a happiness? No. Okay. So you have to make the decision whether or not take it all now or take it later. Okay, let's take a look. If the gain is concave, then here is your initial $100. You should probably draw it properly. So let's say this is $100. And then we have to split it up into, let's just put $200 right here. No, 200. Because the property of prospect theory, and also this prospect theory function, that, let's say this is V of 100. So V of 100 must be greater than V of 200 minus V of 100. So this length, green, is greater than this red. Okay. The more value we have, the less additional happiness we're gonna get from that. So with that property, we can conclude that if you take 12 installment at a $100, that reset every month, you're gonna be happier than V of 1200. So 12 times V of 100 must be greater than V of 1200. Does that make sense? I think the last session I was talking about this like your reference point resetting. So in this case, the problem set is a reset every month when you receive your salary of M. But it could be with anything, right? It can be with poverty as well. Like the money that you lose, but you reset, right? Yeah. Okay. Yeah.
Is that also because of diminishing marginal value of the concave function?
Yes. It's like every additional dollar that you gain, it's gonna be less than the initial one, right?
Yeah, that makes sense. Thank you.
I think this question we're gonna see like when you lose money. So we're almost there. Let's go B. Yeah, did I answer question 1? Yeah. I think question 1 you need to like kind of explain why is V of 1200 is greater than 12 times V of 100, which is the property of the prospect theory, right? Okay. Let's go over B. Suppose on January 1st, Big's employer tells her that there have been a budget cut and she needs to take a pay cut of 1200 this year. Would she rather take the entire pay cut this month or take the cut $100 installment over 12 months? Okay. Oof. So we have to like pay cut. So now 2. Same thing as the previous one. So every month with sum of I equals to 0 to 12 with a V of 100 of I think I can be just like here. Like put an I here. No, the I should be in the box. That's a wrong notation. Which equals to 12 times V of negative 100. And big. Now would be V of negative 1200. So in this case, we need to make a statement about why is V of negative 1200 is greater than 12 times V of 100, negative 100. Right. So let's look at it in the graph. So if I lose 100, let me just draw in proportion. If I lose 100, it's not right. So if I lose 100, it looks like this. This is our negative V, well, no. V of negative 100. Okay. So that's our 100. What about our 200? Negative 200. 100. Negative 200 looks like this. V of negative 200. So as we can see that the additional money loss, it hurts us less than the initial one, right? So this gap is our, well, we can imagine this to be like this utility, right? So the additional dollar that we lost at this point on, it's going to be less than before. My iPad is just like weird. Right. Can you guys see this line, the red line? So that's like the average dollar of value that's lost. And then from here to here, it looks like this. So the dollar just become like less and less, like additional dollar loss. It's like hurt you less and less. So of course, that V of negative 1200, it's gonna be greater than 12 times V to the negative 100, right? Does that make sense?
Is that because of diminishing sensitivity to loss?
Yes. It's kind of like, how do you feel about like losing $1 right now? And comparing that you already lost $1 million, and then what's the additional dollar loss to you now, right? If you already lost $1 million, you don't care about that $1. But if you haven't lost anything, that $1 loss is actually valuable, right? Like for example, you go to a halal food truck and then I just need $1 to get a soda or something, right? Yeah. But if you lose like $1,000 in the stock market, it's like, okay, it's okay. Yeah. Okay, so that's the pay cut. You would rather to take a big hit now instead of like having this pain to bled through every single month, because that will hurt you more. Okay. We're good on B. Let's do C. Now suppose the employer tells her that her annual salary remains unchanged, but because of cash flow problem, she's going to get an alternate bonus and pay cut over the year. So 100 bonus on January 1st and $100 cut on February 1st, and so on and so on. The employer tells her that this should not affect her total utility over the year since her overall income remain unchanged. Should Big satisfy with this explanation? Okay, I'm just not gonna solve it, but let's look at this graph, right? So the average, I'm just gonna use like bright yellow green. So the average dollar for gain, like you can see the slope, it's very different, right? There's a steeper curve in losing money than gaining, right? So if you're doing the alternate method, it will look like, so let's say you start with $100 bonus. So V of 100 plus V of negative 100. Like this does not equals to 0. It doesn't balance out. right? Because the average dollar per utility, per value, I guess. Is different. Right. So the V of negative 100 is steeper. So therefore, no, big should not satisfy with that explanation. Because overall, 6 times V of 100 plus V of 6 times V of negative 100 will be equals to, will not be equals to 0. Even though her income didn't change, she will not do it because it hurts her more by losing that $100. Okay, let's go to D. Let's assume the following value function for big. V of x equals to square root of x if x is greater than 0, negative 3. Okay, so this is similar to your homework problem. Okay, so graph this value function. Let's do it. This time, let's do 100. Just try, like when you like doing graph on the exam, if you have time, draw them proportionally, if you can, because it might give you insight towards the question. But if you don't have time, then it's okay. So this is plus 100. Let's see. So if I'm, for x, I have 100, 0, negative 100. If x is greater than 0, greater than 0, then it's this. So I'll have a box here. So if it's greater than 0, I have square root of 100. If x is less than 0, then I don't have this box. I have 100, negative 3. So we have 10 units. And we have negative 30. Ideally, you should probably add maybe one more point, like something like 400, something easy, so you can get the number. So this will be 20. And then if you put 400 here, it will be negative 60. If it's negative 4. Oh. So as we can see, this is concave and convex function. Negative 60. Oh, that's so long. 60. Hmm? Yeah, something like this. Okay. So you graph, that's it. So let's look at E. Suppose an entrepreneur approach Big and offer her insurance against the fluctuating income stream. The employer will pay her $100 in the month when she gets a cut, and will take away $100 in bonus when she gets a bonus. So Big's monthly income will stay constant at M. To get this service, Big would have to pay monthly fee of F. What's the biggest value of F she willing to pay? Okay, the police to get out of the situation, or you sacrifice some S amount of utility by going to some whatever facility. Yeah, something like that. I can't remember exactly. I didn't go through it. But like learn how to like draw this tree is really beneficial on the exam, especially in behavior. The trees and the table. But yeah, any other question, or do you guys want me to go over some homework, or maybe homework 4? Okay, maybe since we haven't have an hour, let me just go over question 1 with a risk premium on this, because I actually have a good intuitive way to kind of like get the R value. Better than this, whatever the things I'm working on. I'll work on that. But do you guys want to do it, or should I save it for tomorrow? Homework 4? Okay, I'll go over question 1 then. Since question 2 is fairly easy. Okay. Utility function, question 2 I can go over tomorrow. So has a utility function over money each month. If he has a X dollar, utility of X equals to square root of X. So job equals to I. Mother equals M. So 2 type of scenario. So P is getting fired. If you're getting fired, you have you only have your mother's income. Well, your mother's money. Supplemental income. And then you have 1 minus P, where I plus M is your total outcome. Okay, so A, expected value of mu. So this is mu. Mu is equals to expected value of X, which equals to probability of getting fired times M plus 1 minus probability of M plus 1 I. So that's A. B. What's the expected utility? So expected utility would be expected utility of U equals to P times the probability, or no, probability of getting fired and the utility of the fire. So that would be P and M to the 1/2 plus 1 minus P to the M plus I to the 1/2. So risk premium. Let's do C. The fun part. C. They seem happy as the gamble. Then the risk premium. Oh, okay. What's the risk on risk premium? Or subsidized. Okay, so here, let's just draw that graph again. So U of X. This is X of certain wealth. And then we have mother's money and mother plus I. And then we have this is utility of M plus I. So let me just make it bigger. So this is U of M plus I. This is U of M. Okay, so if the function, utility function looks like square root of X, so every unit I increase, it's concave. I should probably concave a little bit more. Something like this. Let's just assume this is the concave. I'm not going to try to draw it exact. And then we have expected value. So expected value will be in green. Expected utility. And red is U equals the square root of X. Okay, so we calculate that mu is our expected value of some like monthly income, right? So it's probability of n plus 1 minus probability of n plus 1. So that's mu. That's our mu. And the and the utility of that. So utility of mu is equals to mu minus r. So we know that this black line is r because that whatever the amount that we're like the maximum of money that we are willing to pay to get this insurance, it must equals to our expected utility of mu, right? The utility of mu. So we have point A1, A2, well, point A3. So A2 is our utility of mu. That's the expected utility. I'm crazy. Expected utility of mu. And this is utility of mu minus r. And then point A3, it's when we have uncertainty, which is U of mu. Can we see the difference? So U of mu is we can get that mu amount for 100% certainty. And expected value of utility of mu is lower, right? And we have this A2, which is utility of, well, 100% certainty of mu minus maximum willingness to pay. Does it make sense? Because this two points line up into this red graph. So the red, it's 100% certainty. Your utility of 100% certainty. Right. So the EU is the probabilistic model. Right. Okay. So let's do the setup. Utility of mu minus r is equals to expected utility of mu. I make a mistake again. All right. Okay. I'm hearing nothing. How's everyone doing? Right? So it's the same thing as our formula. Yeah. Ah. Guys, talk to me. Confused? Anything? Because you don't need to remember the formula anymore, as long as you get this graph.
Yeah, it makes sense.
If it doesn't make sense, please tell me. I'm trying to improve. Please.
It does make sense. That's what I'm saying.
Okay. Okay. Zach?
No, I was just going to agree. Makes sense.
Like if you get this point, like if you get the intuition of those points, this is actually a really simple problem. Right? Yes, maybe so.
Yeah.
Okay. Great. Wonderful. I'm terrified. Yeah, like I'm not sure how to, like this E is not working. So I'm gonna like bully it and then get a more intuitive graphical representation of what's going on. Until then, I think this is what you need to remember. Well, not need to remember, but if you draw a graph, it's easier. Okay. Do you guys have like specific problem? Yeah, that's my homework from 2 years. 2 years? No, a year ago. It wasn't too bad.
Wait, Andrew, I have a question.
Yeah.
From problem set 4, could we go over question 2 really quickly?
Okay, question 2. Okay,
Yes.
sure. Okay. I think let's just look over my solution, because I think it's clean. It's better than I have to write again. Let's see. Windows. Okay, so question 2. Okay, so Martha, oh, which question specifically?
Yeah, question 2 for part A, when I looked at his solutions and I'm not like understanding the algebra of how he solved for A.
Okay. Okay. How about we just start clean instead of looking at my ugly homework. Okay, so A, you have Martha. And then the utility is equals to W of A. So W is wealth. And A is just some coefficient. Okay. And A is a positive number, blah, 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 blah. For which value of A will she take the bet? Take the bet. Okay, so now you have two situations, whether or not you take the bet or not take the bet, right? So here we have a bet. We have here, not bet. Am I the only one in Hunter is sick? No, right? Okay. So she has $20. So wealth, it's how much money that she has, right? So if you don't bet, your whatever outcome is $20 to the alpha, right? So U of not bet is equals. I feel like every time I write something, it's gonna be like so different. Okay. And what about your utility of bet? All right, so your utility of bet is the probability so it's a coin flip, right? Coin flip. So here we have 2 more line. So you have a lose and you have a win. All right, so lose with probability of P and then win of 1 minus P. All right. And then you have a utility of what? If you lose.
0.
0 to the alpha, right? So this is W, what, U of lose. U of win is 98, right? Because you win that, so 20 plus 70 of A. Okay, so now we just, so when will she take the bet? So
1/2 90A.
Huh?
1/2 90A.
Oh, I haven't done the probability yet.
Oh, okay, I'm sorry.
No, yeah, you're fast. Okay, so utility of not bet. Oh, wow. So in what condition will you bet? Will she take the bet?
If the utility of betting is bigger.
Right. So utility of bet is greater than utility of not bet, right? So what's the utility of bet? Utility of bet is probability of utility of lose, which is 0, A, plus 1 minus probability of utility of win. So utility of lose, utility of win, so 98. And then it's greater than 28, right? which is utility of not bad. Okay. And we have a 0. And we have a probability of 1/2, right? Plus 1/2 of 98 greater than 28. Okay, that's it. So 0. And we have 1/2 of 98. We can't distribute that thing, right?
Yeah, this was the part where I got confused because he just got like a equals 0.46, but I don't know how he got there.
Right. So let's do ln, right? We can do ln. Okay. So what's how are we supposed to do the ln? So let's split them up. It's like I don't know, 1/2 plus ln, well, of 90. So the a comes down greater than a of ln of 20. Right? So if you take the okay, so if you take it ln of this thing, right? So 1/2 it's times this thing, right? So if it's times, if you're doing ln, then it's plus. Right? So it's ln of 1/2 plus. So if you're doing ln to the 90 to the a, so it goes up here and goes down here. So your a just go into the front, and your 90 is your base. So it's a of ln of 90. Yeah, that's it. Does it make sense? Just me saying.
Yeah, that part makes sense. But like, what do you do after?
Huh?
Like, what do you do after? Because he like was able to get like a number
Yeah,
for
yeah, yeah.
A.
Yeah. So I fully understand. My math is really bad. So I don't even know how to take ln back then. But I think like now I'm like better. But okay, so let's solve for a, right? Okay. So let's single the a out. So we have an ln of 1/2 greater than a of ln of 20 minus a of ln of 90. Right. We have it's ln of 1/2 greater than a to the ln of 20 divided by 90. Okay. Sorry, I'm cheating. I just need to cheat because I don't want to take out my calculator. So you isolate the a, you move this here. You get ln of 1/2 divided by 20 over 90. Okay, this whole thing. And greater than a. And then if you do that, you'll get so ln of 1/2 is equals to negative 0.69314 and then divided by 1.50404. Yeah. So this is ln of 2 over 9. Okay. And then you get an a. Okay. Oh, I'm sorry. You get an a equals to 0.4608. So if you do ln minus, that's division. If you do ln plus, That's multiplication. So that's like why it's like, yeah. You good?
Yeah, I'm good. That one makes sense. And could we also go over 2D, please? Because I'm not understanding the graph of it.
Okay. So yeah, were you here last week?
I was here last week,
I thought I
but I'm
grabbed
just,
it.
you did, but I'm just so confused.
Okay, so let's do it. Let's just go over two in next 13 minutes. Okay, so let's do B. We have A. Let's do B. So Martha operates according to prospect theory. Okay, prospect theory, easy. Easy. We just put a cross and put a table right next to it. And we have this is X, and this is X greater than 0. This is X less than 0. Okay, so we have X. My nose. So pick easy number. So something can be easy to square root by square root. Square root by square root. So 1, well, I mean 4, 1, 0, -1, -4. Easy to do. So what if X is greater than 0? Greater than 0 is square root of X, right? Square root of X, square root of 4. Square root of 1, 0, leave it empty. Yeah. And then we have a negative. So -1, it's -1 square roots of -2. And then this is -2 square root of -4. Then we graph it. This is equals to -2. This equals to -4. Right? So this is 2, this is 1. So we have X. This is baby of X. This is 1, this is 2, this is 3, this is 4. 1, 2, 3. Whatever. I'm just gonna not graph that point. So we have 1, 2, -1, -2. Right, and then we just plug it in. So 4, if X equals 4, then V of X equals 2. If it's 1, it's 1. So connect them. If it's 1, it's -2. Well, -1. Yeah, -1, -2. Right?
Wait, sorry to interrupt, but in his graph, it looked a little bit different. Like at point 2, it was like a straight line up until the X line was 0.4.
What?
For his graph, it looked a little bit different.
Well, that's continuous, right? This is
Mhm.
estimate 1, right?
Okay, okay.
Yeah. So I'm basically average. So it's derivative. Well, it's integral of 0 to 1 when square root of X. I'm basically doing that. Well, my line is basically this. Wait, no. Anyway, you get the point. I'm just estimating. But if you divide it into infinite, if you put in infinite X here, it should be curving, right? But I'm not. I'm just giving estimate point. Yeah, because there's no way I have enough time on the exam to do that. So that should be your graph. You can just draw like this, like this. Yeah, that's fine. But I don't think it's useful. If it's not useful, I'm not gonna draw it. So this is useful. Just me. You don't have to do it.
Wait, Andrew, sorry. I thought we were looking at 2D. That's why I was confused about the
Oh.
graph. Yeah,
no, we're
2D
going
on
over
fi-
everything. We're going
Oh,
over
okay. Okay, okay.
since we're here already. Yeah. Okay, so prospect theory explain, and will Martha accept this bet? So how will Martha accept the bet? It's when value it's a positive, right? So Martha has a reference point. Reference point it's so V of bet is greater than will Martha accept the bet? So if it's will Martha, then value of bet minus value of not bet should be a positive number if she bet. So we set them equal to 0. So value of bet is I mean, you can put the 20 there, or you don't have to. I guess like let's try to put 20. Oh, what's going on with 20? But I think they cancel out, so it doesn't matter. So you start with $20 and then you do value of bet. So plus value of bet is if you win is what? Square root of 70 and minus 2 of square root of 20. I'm having a weird feeling, but it's all right. Let's keep going. Minus value of not bet, which is square root of 20. Yeah, they cancel out. It's okay. So square root of 70 minus 2 of square root of negative 20. Right. And that should be it. And then you get answer of negative 0.292. Okay, sorry, I cheated. Just don't want to do it. D. Now it's the weighting function. So we have a pi of p. So p is probability, right? And 0.2, 0 greater than p greater than 0.4, p minus 0.2, and then we have a 0.4 to p to 1. Right? So probability, the total probability will always equals 1. So, okay. So now, so how do we make the graph? So in order to make the graph, we need to actually plug in. Sorry. So P. Let's do 0.1, 0.2, 0.5. Well, let's do the point, right? 0.4, 0.4, 0.5. And then, yeah, whatever. So pi or equals to what? If p equals 0.1, so it's 0.2, 0.2, 0.2. If it's 0.5, it's 0.3. If p equals to 1, then pi of 1 equals to 0.8. Okay, we have all the points. We just need to draw. So p, pi of p. So this is 0.2, 4, 6, 0.8, 1. Okay, let's just do it here. 1.2, 1.4, You get a juice. Okay, so let's plug. So if P equals 0.1, it's 0.2, right? This is P. X-axis is P. So if it's 0.2, it's still 0.2. If it's 0.4, still 0.2. So you draw a line here because probability is continuous. Well, I mean, it's not continuous, but the weight of probability is continuous. Because you can have a probability of 0 point something, and then you will still have a weight of 0.2. Okay, so you have 0.5. Well, if P equals 0.5, so 0.5 is here, you get 0.3. 0.3 is here. Just connect them. And then if you have 1, you get 0.8. Okay, that's it. That's your weight. So this red line is your weight. If you have a 1-to-1 weight, then you have this blue line. Okay. So now, will Martha accept this bet? So this will be probability of, well, let me, pi of P times value of X. Oh, this is win. This is win. Well, win plus pi of lose V of X lose. Okay. Pi of 1/2 is what? Half 1/2. Well, no, not 1/2. Wait, is it 1/2? No, it's 1/2. So it's 0.5. So P is 0.5, it's 0.3. So 0.3 times V of winning, it's 70, plus 0.3 V over -20. Is that the case? And then equals to some number. And then you get that number equals to negative something. And then no betting. Okay. Does it make sense?
Yeah, that makes sense. Thank you.
Okay. Well, data talk. Any question?
I had a theoretical question, but
Yeah.
so can I ask that quickly? Weighting functions generally, if it's medium to high, I think I was reading that they're underweighed as opposed to low where they're overweight. Is that right? The probabilities, if they're high, they're underweight.
High, you are underweight, and low, you overweight. Is that what you're saying?
Yeah, I think that's what I read in the paper, but I wanted to make sure I wasn't misreading.
Yeah, I think that's in generally it's true. So here it's like if we have a 1-to-1 weight, right? 45 degree, not 40 degree. But like I think it looks like this. Because if it's 0, we're weighting 0. There's no way we're gonna weight that thing. If it's if there's 100% probability of that thing, it's not gonna happen. So it always starts from an origin. It's kind of like this. Do you see what I mean?
Yeah, it's kind of an S shape.
Yeah, something like that. Yeah,
It's kind of like convex and then it becomes concave almost.
yeah, something like that. Yeah.